Good afternoon. I apologize for the minor technical difficulty there. We're going to be starting the webinar right now after a brief introduction. My name is Dennis Keene. Appreciate everyone joining us for this webinar on PFAS remediation. I'm a senior project manager here at XDD Environmental. Today's webinar will be focused primarily on existing remedial options for per and polyfluoroalkyl substances. The presentation will be divided into three sections. We're going to have the first presentation will be completed by Dr. Ellen Moyer, who will be presenting some of the general chemical properties of PFAS and how they impact remedial technology selection. Michael Marley will then give an overview of the current state of remedial options for PFAS that have been shown to be effective. The final presenter, Dr. Raymond Ball, will give an overview of the oxidation process for treating PFAS. Total length of the presentation will be about 50 minutes long with a 10-minute question and answer period. We'll try and make up some of that time towards the end due to the delay. Please enter your questions during the presentation, and we'll get as many as possible done during the question and answer period. Just also, we'll be sending out a copy of the slide material to the registrants after the webinar concludes. That's my introduction. I'm going to skip over the agenda here since I've given most of it to you already, and we will get going with Dr. Moyer here. So give me 1 second here, and I'll hand that over to her in 1 second.
Thanks, Dennis, and it's so great to be here. Thanks. So PFAS are per and polyfluoroalkyl substances. They're a diverse class of chemicals that contain carbon-fluorine bonds, and these bonds are extremely strong and stable. There's not good agreement on just what exactly is included in the term PFAS. It's at least several dozen chemicals, and by some people's reckoning, far more. So this is all being worked out. Many of the PFAS are carbon chains of varying lengths, and the ones with the per suffix in their name, they have all their carbons fully saturated with chlorine. The ones with poly in their suffixes are ones in which not all the carbons in the chain are bonded to fluorines, and they might be bonded to oxygen, hydrogen, sulfur, nitrogen, or other atoms. What you hear about mostly in the news these days is PFOA and PFAS, and both of those chemicals have 8 carbons, and you can see a diagram of PFOA on the slide here. In general, PFAS are water-soluble, not all that volatile, and as far as we know, resistant to biodegradation, but a lot of research is being done right now, so that may change. And certain chemicals can degrade to PFOA, so one needs to look for parent compounds if PFOA is in a sample. Can you advance? Yeah. So this slide summarizes the chemical and physical properties of PFOA and PFAS, and they're compared to benzene so you can get a sense of what the numbers really mean. And there are a lot of question marks about the chemical and physical properties of other PFAS chemicals. So, but we do know quite a bit about these two, at least. For molecular weight, we can see that these chemicals are heavy and large. So this is favorable for the prospects of filtering these chemicals out of water. They also have a pretty high boiling point compared to benzene. So this suggests that if thermal methods are going to be used, you might need to apply some pretty high temperatures. The vapor pressure values measure the tendency of the chemicals to volatilize from the pure phase to the air phase. So with these low vapor pressures, it suggests that technologies such as soil vapor extraction are not going to be very easy to apply. Henry's law constant measures volatilization not from the pure product phase, but from the dissolved phase to the air phase. And the constants are so low that they're not measurable. What this suggests is that the chemicals want to stay in the water and not partition out into the air phase so that technologies like air stripping and air sparging are not going to be very favorable. KOC is a partitioning coefficient measuring the adsorbed concentration divided by the dissolved concentration. And you can see that the KOC values are greater for PFOA and PFAS than benzene. So benzene adsorbs pretty well, so PFOA and PFAS would tend to adsorb even better to things like carbon. And then finally, PFOA and PFAS have solubilities on the same order of magnitude as benzene, so this suggests that these chemicals are going to dissolve into water, which they do. PFAS are widely used in our modern life. They are resistant to heat, oil, grease, and water, so they have a lot of applications. They're used in industry and consumer products since about 1950s. And the products usually contain a mixture of PFAS chemicals of varying lengths and impurities. So you may be familiar with Scotchgard and things like that that are used to waterproof clothes, non-stick cookware, Teflon that is in sampling equipment, takeout containers, a lot of different products. It's also used for wire insulation in paper and paints, firefighting foams. You can hear about a lot of sites around that are caused by firefighting training areas, and they're also used in carpeting and furniture. PFAS are found worldwide in the environment, wildlife, and humans. They're even found in the Arctic and Antarctic. And a 2015 study showed that PFAS were found in 97% of human blood samples that were tested. The widespread occurrence really came to light as a result of Safe Drinking Water Act testing just a few years ago. And PFAS were found in 66 water supplies serving more than 16 million Americans in 33 states. And these cases had at least one sample at or above EPA drinking water health advisories. Now, concentrations of concern are very low for these chemicals. And as a result of that, it's common to see large dilute plumes of PFAS at concentrations exceeding safe levels. So it's an extremely challenging problem just because of the sheer volume of water that's involved often. And there are a lot of difficulties in sampling due to the need to get down to low levels and to avoid cross-contamination from things like Tyvek suits or Teflon sampling gear. So a lot of care has to be taken to get good samples. And then there are also challenges in laboratory analysis, getting down to the low levels of concern and also detecting all the chemicals of concern. So generally, a couple dozen chemicals are detected and quantified by commercial labs, but there may be more that we need to worry about. So most of the concern has been with the longer chain PFAS, C8 or greater, and specifically PFOA and PFAS. These chemicals persist and travel long distances, and they do bioaccumulate. The potential health effects are being studied, so there is some controversy here, but potential health effects include effects in development of fetuses and children, including learning and behavioral impacts. Also impacts on fertility, hormones, cholesterol. They can suppress the immune system and increase cancer risk. And here's a little video that was made before the health effects came to light. this is a little party where the students are being sprayed with firefighting foam and having a great time, not realizing they're being sprayed with carcinogens.
Yeah, well, the video isn't available right now, so we can release that when we actually distribute later on to everyone else.
Okay. So EPA has established health advisories for PFOA and PFAS at 90 nanograms per liter, that's parts per trillion, either individually or combined for lifetime exposure from drinking water. And this is based on lab studies of rats and mice and also epidemiological studies of exposed human populations. Unfortunately, EPA has no plans to establish MCLs, but they do plan to develop regional screening levels for site cleanup. So help is on the way here. States have begun to establish standards. Some states have no standards. Some have standards for PFOA and PFAS, and then other states have standards for other PFAS chemicals. So it's a real heterogeneous situation. So now Mike is going to talk about the technology toolbox and what is available for remediating PFAS.
Thank you, Ellen. Again, as one would expect, there's a lot of research and development that's still ongoing with regard to PFAS, and therefore what we're presenting basically is the current state of technologies as we understand it. It's not fully encompassing. I'm sure there's other research that's going on for different processes, but what I've highlighted here is some of the technologies that have some degree of demonstrated success in treatment of the PFAS materials. They're split into the 4 different categories: physical treatment or physical removal. As Alan mentioned earlier, because of the molecular weight of the PFAS materials, some of the filtration processes and reverse osmosis processes are capable of high percentage reduction in their chemical concentrations in water, greater than 90%. And we'll talk a little more about that in the following slides. Similarly, again, as Alan pointed out, that some of the characteristics make it amenable to adsorption or ion exchange, and we will talk a little more about those in detail in the following slides. Obviously, excavation and disposal is always available for these. Again, the disposal, because of the stable nature of these contaminants, you need to look at something that's got high energy to dispose and destruct of the chemicals of concern. And in situ stabilization, again, with regard to isolating it from the environment with regard to leaching. Chemical oxidation, I think, basically is one of the more interesting technologies in the fact that it can be applied in situ and ex situ, and there's been quite a bit of work done on it, and with varying degrees of success. There's been a variety of attempts with different oxidants, and I think the common theme that you'll see when we get to it is some of the more complex chemistries where you're adding a mixture of oxidants that basically can produce a wide range of radical species, both reductive and oxidative, have had more success. Some of the more ex situ approaches, such as senolysis, which is an oxidation technique using peroxide in the presence of ultrasonic, that basically has had success, and similarly photocatalytic in the presence of an oxidant, again, has had success in destroying the PFAS. Most of these studies have looked predominantly at the PFOA and PFAS, and again, I'm sure there's research going on looking at a wider range, and Raymond will be talking later about his study, which encompasses more than the PFOA and PFAS. Biotransformation is interesting. I'm a big believer in the fact that Mother Nature will find a way to destroy these contaminants given enough time. There is a number of literature out there, and basically one of the confusing things, and Alan touched on it earlier, is that some of these polyfluorinated, not the perfluorinated, but the polyfluorinated, have been measured to change in composition or be degraded under low energy conditions such as natural attenuation. And we believe what's happening there essentially is some of the fully saturated carbon fluoride bonds basically are being able to be transformed into a different PFAS material that basically is not, the PFAS is not going away, it's been transformed into a different form. The general wisdom is that they basically will accumulate as the perfluorinated under those circumstances. There is a study that I did read where they've done anaerobic biodegradation of PFOA and PFAS, and in the experiment they did see some reductions in the total concentrations, but there was no fluoride detected in the reactor as a result of this, again suggesting that any decrease was probably the formation of another polyfluorinated or perfluorinated compound. Some of the other technologies, as you would expect, high energy technologies such as high temperature will obviously destroy or break down these PFAS materials. Obviously, you'll end up with fluorine, fluoride, basically that has its own issues to deal with, but these can be broken down under high temperature conditions. Another, again, high energy conditions such as electrochemical, where they've used mixed oxide metal anodes in the groundwater samples and been able to destroy, break down, and form the fluorine fluoride breakdown products. This is taken from literature. The reference is given here, basically, and this was a study looking at ex situ water treatment options, and it sort of validates some of the stuff that I mentioned in the previous slide, where the adsorptive technologies such as ion exchange, granular activated carbon, filtration like nanofiltration, reverse osmosis, showed success with those treatment of the PFAS materials, whereas some of the aeration technologies, coagulation, and some of the more basic oxidation technologies such as permanganate, oxygen, ozone, by itself had difficulty in achieving significant reduction. I'm going to talk in a little more detail about 3 different technologies before I transfer over to Raymond. Basically, we'll talk a little about filtration, we'll talk a little about adsorption, ion exchange, and we'll talk a little about the chemical oxidation in a little more detail. With regard to filtration, I'd mentioned that the molecular weight cutoff, or the definition that is typically out there, that defines the molecular weight in terms of Daltons, which is a Dalton's about 1/12 the mass of a carbon atom. And so because they're fairly large molecules on the order of 300 to 500 Daltons, and nanofiltration typically will be able to filter out anything more than 200 Daltons. Basically, it can be very successful. Now, ultrafiltration and microfiltration doesn't have that level of reduction capability because basically the filters are larger, but the nanofiltration has been shown to be greater than 90% effective as an ex situ treatment technology. Similar to reverse osmosis, the polymers that are typically involved in the formation of the filters again have larger capacity to remove higher molecular weight compounds, and again they're going to be expected and have been demonstrated to be greater than 90% effective for most of the PFAS materials. The one thing about this technology and also the adsorption-based technologies is you aren't reducing the PFAS material, you aren't causing them to be transformed. They're essentially been retained, and you're reducing a waste stream. And those waste streams, depending on the methodology, can be significant volumes still relative to the original stream, and you do have a concentrated waste stream that you need to deal with. And again, people are looking at different and researching different techniques. Obviously, thermal techniques can be used, but some of these electrochemical techniques and other techniques that can be used to destroy these concentrated waste streams. Adsorption and ion exchange, I think, is very interesting. Again, a non-destructive technologies, but I think it's predominantly the go-to technologies for today. What we're looking at Carbon-based systems, obviously, predominantly we've got ex situ activated carbon GSE systems, and as I mentioned here, it's the current go-to approach. And there is a number of in situ injectable carbon-based systems that are out there also. Again, the caution obviously with these systems is that basically you're removing it from the water, but it is a reversible process. There is a capacity limit, and therefore you have to be aware of the design to make sure that you're covering enough product to basically absorb the mass flux that you're dealing with over the time frame that you want it to act for in situ. There is other non-carbon-based systems that are predominantly clay-based or a blend of absorbents. Clay is combined with other absorbent materials such as Remedial or Matière. And there's ongoing research looking at zeolites as a potential absorbent for PFAS. The R&D is really focused on the fact that these are very cheap. Zeolites are very cheap. They're naturally mined. And therefore, if they were to work and have decent absorption capacity, they could be competitive to some of the other absorption technologies. I think one of the most interesting is the research that's going on with synthetic resins. And so that, which we're going to talk about in more detail in the coming slides, is gaining a lot of traction, predominantly due to the fact that you can manufacture these resins to be absorptive of a number of different chemicals, including PFAS materials, and therefore you can generate a lot more capacity and effectiveness with these resins. They're typically going to be more costly on a pound-for-pound basis, but definitely have attractive aspects too. Next slide basically does just a general comparison for carbon-based systems versus these ion exchange resins. Again, not all carbons are created equal. Basically, the source makes a difference, the manufacturing process makes a difference as to the capacity for absorption, the uniformity of the absorption surfaces, and the hydraulics of flow within these carbon beds to make sure you're maximizing the contact with the active sites. It's been proven. It's the technology that's out there as the go-to. It's been effective at multiple sites throughout the country and definitely been considered and used for these point-of-entry treatment systems. Regeneration, again, it absorbs the PFAS, so the carbon is going to be regenerated. Typical regeneration is at high temperatures in the excess of 1,000 degrees centigrade to destroy, quotations, the PFAS, because again, we don't know how much destruction is occurring. We know that we're not destroying fluoride or fluorine, but are we forming byproducts or breakdown products that need to be considered? That's still an area of question with respect to some of these removal technologies that are still out there. It does have a lower capacity than the resins, and right now there's a big question mark on its effectiveness on some of the shorter chain PFAS that are out there, but there is still a bigger question on whether there is a similar level of concern from a toxicology perspective and a mobility perspective of the shorter chain PFAS materials. Obviously, carbon can be cost-effective and is used. It's really a site-specific analysis as to whether it's going to be the best choice for a specific site. Typically, from what I've seen, shorter duration operations, lower PFAS concentrations, less interference from other groundwater constituents such as natural organic matter can all lead to maybe making the carbon more cost-effective. The alternative adsorption material that is out there being used more significantly in the last few years is these ion exchange resins. The number of case studies is increasing, and because you can manufacture these resins to higher capacity for particular contaminants, it does have a much higher capacity. There is a lot of research and development going on with these resins, in particular looking at things such as the shorter chain PFAS compounds, removal. There's also research going on regeneration and removal mechanisms. Again, when you do this process, you're going to be left with a waste stream. If there's work going on to see if that waste stream can be removed while in in location, on location, by mechanisms that are being incorporated into the full treatment process, such as some of the processes that we've talked about, such as electrochemical. Treatability studies are essential for all these technologies, regardless of carbon or chemical oxidation, because there's such variety of PFAS materials out there. There's such variety of natural materials in groundwater and in soils, obviously, that can affect these processes. So treatability studies are essential. Even for a simple carbon system, it's recommended that you would do treatability to determine the right design, right loading of these compounds. A couple of slides provided by Steve Woodard of ECT Squared, who basically is in the leading front with regard to the resins. And I know he's working with a number of universities out there and other entities, basically continue looking to improve the performance of the resins and to incorporate other blend of materials, non-resin materials, into, again, take care of the wide variety of chemicals that are coming through in these groundwaters. So this is an example comparing the Filtrazorb, which is a Calgon carbon product, to the resin, this particular resin Zorbex. And it's a 5-minute empty bed contact time in these ex situ reactors, and both are very effective. Both are very effective at removing the PFOA in this particular case down to very low levels. The difference, again, as we talked about, is the capacity. You can see that the resin is capable of retaining, without breakthrough, for about 15,000 bed volumes, whereas the activated carbon will get breakthrough in a few thousand bed volumes. Still substantial, but a significant difference and needs to be factored in the overall costing of the process. Similarly for PFAS, basically, again, the influent concentration you can see in about 25 parts per billion. A very similar story. The resins are very effective over a much larger number of bed volumes, whereas the carbon, again, is very effective, but has got less capacity for the before breakthrough occurs. Okay. This is from the same study, basically looking at a mixture of PFAS materials coming into both the carbon reactor and the resin reactor, which are split off from the feed. And again, you can see a similar story in that the resin, as expected, would have a much greater absorptive capacity, much larger capacity for bed volume throughput versus the carbon. What's also interesting from this slide is basically the variation in the absorptive capacity, in particular for the resin, for the different PFAS materials. And again, I think that's one of the reasons why the research is ongoing, looking at combinations of resins mixed with non-resin material that basically can be more consistent on the high level capacity for the treatment of PFAS. One of the benefits, again, of the resin is you're not regenerating it at a high temperature, and therefore its regeneration capacity is expected to be pretty close to the original capacity, and that's what this particular slide shows. It shows basically, again, that the once regenerated, the resins basically have a very similar capacity. One of the interesting things I learned from talking to Steve about the technology is it's not just an ion exchange process that's occurring on these materials. It actually is a combination of absorption and ion exchange for chloride ion for the ion exchange portion. But there's also quite a bit of absorption going on because of the structure of many of these PFAS materials. Such that it's interesting, one of the things that Steve mentioned is in trying to regenerate, if you use just a typical brine wash, it's not going to work very effectively on the regeneration because of the absorptive portion of the PFAS materials. And similarly, if you just use a desorbent like a methanol, for example, you may not get effective regeneration because you may not affect the ion exchange portion. So very interesting, and a lot of research ongoing in that area. My last slide before I turn over to Raymond, who will give you some specific case studies on the use of chemical oxidation. Several bench studies, including work by XDD and others throughout the country, both at the university and in the practitioner, there's been a lot of work going on looking at this, and it's been focused on primarily on PFOA and PFAS, because those are the ones, as Ellen mentioned, that are most in the news, but they've also been dealing with other PFAS materials. And generally, there's been a lot of partial success to full success in these bench studies. There's a lot of practitioners out there who at the moment are publishing on their particular blend of oxidant or oxidants that basically are having success. And there's quite a few of them that have popped up in the last few months. I've seen 2 or 3 new publications associated with different combinations of oxidants. The common theme that I've seen basically in the chemical oxidation approaches is that it requires the higher level of success has been observed when using more complex chemistries. In other words, combining oxidants such as the ozone and the peroxide, or the ozone peroxide persulfate, or persulfate with heat activation, or persulfate with alkaline activation, or peroxide activation. So some of these more combined oxidants where you form a suite of radical species with reductive radicals and oxidative radicals, these are the ones that have shown, and it's the ones that we have seen success in ourselves over the years. Basically, they have that capability of breaking down a lot of different compounds and creating these PFAS materials. There has also been success with oxidation processes, and we named some of them before with the electrochemical oxidation and the phonolysis and the photolysis. But even with something simple like permanganate, when you add in additional energy such as higher temperature or higher temperature and pressures that have been done with some of the peroxide-based chemistries, you can basically also get the removal. Question is, are they going to be practical for, obviously, not so much for an in situ application, but potentially for an ex situ? Obviously, that comes into cost analysis. Again, treatability studies, very important to make sure that you're removing the target contaminants, you're not forming something that is of more concern. So again, treatability studies are very important with regard to chemical oxidation as well as with the adsorption technologies. I'm now going to turn it over to Raymond, who's going to give you some specific case studies that he's been involved in. Raymond, you're up.
Thanks, Mike. The technology I'm going to talk about is called Oxizone. Oxizone is a peroxone-activated persulfate-based oxidant mixture. Oxizone has been in use now for several years on more traditional contaminants, chlorinated solvents, petroleum hydrocarbons. It's been used in and around buildings. And then more recent, I should say that it is applicable both in situ and ex situ as a technology. And more recently, our work was focused on an Air Force base where we were looking at treating a mixture of organic waste in situ. And it happened to be at a fire training area. And of course, at the fire training area, lo and behold, the PFAS compounds were detected. And fortunately, we detected those early on in the study, and then we tracked those throughout the study. The study was basically a field demonstration of the technology, not designed to completely clean up the fire training area, but yet to test the technology and demonstrate that it could be used to treat mixed organic waste. And this is the start of the case study. The site was in Virginia at Joint Base Langley Eustis. There was a history of using aqueous film-forming foam at the fire training area. And on this slide, it's an aerial view of the fire training area. Within the fenced area was where this fire training area was. The investigation that we did at the beginning of the study showed that we had several chlorinated organic compounds, of which trichloroethane was the dominant compound. There were other compounds, petroleum-related compounds, and there was actually 9 detected PFAS compounds. At that time, the analysis for PFAS could detect 14 compounds, and we actually found 9. PFAS was the dominant compound of those 9 PFAS compounds. The ranges that were found of PFAS and PFAS are shown here in this figure. And I should say that there was residual NAPL, primarily as trichloroethane, throughout this site. So the PFAS that we were tracking was in the presence of much higher concentration organics. Again, the PFAS here is in the parts per billion range, and you have the other contaminants that were in the milligrams per liter range. I should say that the geology was fairly complex at this site. And next slide. At the beginning of the study, we did a membrane interface probe investigation to see what we were up against. And these are some of the results showing the distribution of primarily chlorinated organic compounds. This is the chlorinated organic compounds detected using membrane interface probe with a photoionization detector. And on the left-hand side of this figure, you see a plan view on the top and an isometric view on the bottom. And that is the pre-injection results. On the right hand of the slide, again on the top, you see the plan view and the isometric view post-injection results. So what you see here, this slide is showing you basically it's from the groundwater surface, which was very shallow, about approximately 2 feet below ground surface, down to about 24 feet. So what this slide is showing is a great reduction in the overall amount of chlorinated mass after the injections. Again, the idea was to demonstrate the technology, not to clean up the entire site. The time and budget to clean up the entire site wasn't designed for that. But this shows that a very large reduction in the overall chlorinated mass as a part of the study. This is then focused on the PFAS and the PFAS and the PFAS reduction throughout the study. If on the upper slides are tracking PFAS compounds, the 9 detected compounds from the pre-injection to the post-injection. And then on the bottom of this slide, we're showing PFAS, only PFAS. PFAS was the dominant compound of the 9 detected PFAS compounds. So what you see, and these are isoconcentration contour maps. The warmer colors, the reds, are higher concentration. The blues are the lower concentration. So in the upper sequence, you see pre-injection, some orangish colors, then post-injection, 2 months post-injection, and then 6 months post-injection, you see going to more blues. The injections occurred, you see down at the bottom of the slide, it tells you in the late April to August period. So we have the sequence of pre-injection in April, and then 2 months post-injection in October, and 6 months post-injection in September. The slides on the bottom or the ISO concentration contours on the bottom of the slide are for PFAS only. And again, you see warmer colors going to blues. The lines that you see in there, this was all looked at relative to a test cell. The test cell was approximately 20 feet by 25 feet. And so in the course of the study, we looked at all the concentrations from within the test cell as compared to outside of the test cell. Most of the oxidant was contained in the test cell, and so the comparisons for later on were done inside the test cell versus outside the test cell. The field demonstration results for PFAS, when you think of it in terms of lines of evidence approach, what we found was 21 to 79% decrease in the total groundwater concentration of the 9 detected PFAS within the test cell. PFAS was the dominant compound, and we had the greatest reduction in groundwater concentration of all the PFAS. The other thing we found is by doing a statistical comparison of all the data from within the test cell to all the data outside the test cell, we found that the PFAS concentrations decreased within the test cell, but not outside the test cell. It was also found that the groundwater concentrations, based on the conservative tracer chloride, showed no dilution impact from the injections. So after we did the field demonstration test, we went back and tried to convince ourselves using bench testing that what we were seeing in the field made sense and that we actually could destroy PFAS and PFOA. This test was, I should say, this field demonstration testing and so on was, and all of this work was conducted between 2013 and 2015, very early on in the discovery of the whole PFAS problems. So we went back and did bench scale testing, and what you see here is some of those early results of bench scale testing. We've done much more work since then, but these are some of the very first results. So in the upper table, you see spiked deionized water, spiked with PFAS and PFOA. And there's a little bit of impurities in those, quote, pure compounds. But what you see is a very good destruction using the oxyzone technology of about 99%. And then in the table below that, you see this is spiked groundwater again. It's actually PFAS water spiked with PFAS and PFOA and treated with the oxyzone. And here, what's interesting about this table is you see evidence of a sequential breakdown of the higher carbon chain compounds, the PFAS and the PFOA, to intermediate compounds of 6 carbon chains after 3 hours. In particular, you see the 6 carbon acid and the 6 carbon sulfonate increasing after 3 hours, but then after additional continued treatment, 6 hours, you see those decreasing to very low levels. So that by the time at the end of the test, you're actually looking at about in the 90-some% removal range. Then additional testing since that, those the field demonstration tests were continued on, and here we've taken distilled water and spiked it with PFAS and PFOA. And in these tests, we wanted to further convince ourselves that we're destroying the PFAS compounds In these tests, we were actually tracking fluoride. So what this data is showing showing the decrease in the PFAS and the PFOA, and also an increase in fluoride. So the dashed green line at the top of the figure is showing the theoretical mass of fluorine in the compounds, and the solid green line is showing the increase in fluoride anion as the test proceeds. And what you see is by the end of the test, you've achieved about 86% fluoride mass recovery. So based on the decrease in the PFAS, the PFOA, and the increase in the fluoride anion, we're convinced that the technology had the capability to destroy these compounds. Then, adding one more level of complexity, in this test, we took an AFFF groundwater that had many more compounds than PFAS, PFOA, actually many more than what can probably be analyzed. And in these kind of tests, we were at the time analyzing 26 compounds, and again running the test and tracking fluoride. And what you see in this sample is a decrease in the total PFAS based on the 26 compounds. You see PFAS decreasing, and again you also see the fluoride increasing. But in this particular case, it did not, I should say it's compared again to the theoretical fluorine mass. And you see in this case that we've achieved, I believe it's up to about 39% in the time of the test, 39% mass of the fluorine recovery. And then in this test, this is another AFFF groundwater, same kind of a test where we are tracking fluoride and comparing it to the theoretical fluorine in the total of the 26 known compounds that could be analyzed. And here you see total PFAS decreasing, PFAS decreasing, and you see that again the fluoride concentrations this time increasing above the total fluorine to about 750% fluoride mass recovered. And so this is indicative of many more compounds than the 26 that could be analyzed, generating a lot more fluoride mass than the 26 would lead you to believe. So in summary, just summarizing the field demonstration technology, it was based on MIPS. The idea was to try to destroy a mixed organic waste, demonstrate the technology for mixed organic waste, and also track, as it turned out, 9 PFAS compounds throughout the testing. The data suggests that we were destroying both the mixed organic waste components as well as PFAS in the presence of residual NAPL. And then based on bench scale testing that was conducted after the field test, what we see is a decrease in PFAS, and we see an increase in fluoride anion, sort of demonstrating the positive proof that we can actually destroy a wide range of the PFAS compounds. And that all data I should say the testing that was just shown was not optimized per se, but it is believed it can be optimized, and then that these PFAS compounds can be destroyed to very low concentrations. And finally, I would just talk about how we see the technology being used. We see perhaps in a source zone of an AFFF fire training area using the technology for both in situ and ex situ treatment. It could even be used to supplement an existing pump and treat system, maybe where carbon is already, granular active carbon's already been installed. Our technology is definitely can be fitted to an ex situ reactor, and of course it can be used for in situ treatment. We also see maybe the technology being used for in situ treatment more in a dilute plume area, either using a vertical or horizontal wells. So with that, I'll turn it back over to Michael, and he'll give you the last thoughts. Thank you very much.
Okay, thank you, Raymond. Again, I want to thank everybody for joining us on the webinar today. I know with a little technical glitch on sound early on, we've come to pretty much the end of the 1 hour. I would encourage you, we've got questions here. I'll encourage you to contact Alan, Raymond, or myself with any questions that you might have, and we can get to them. I think on the last, finish up basically, obviously there's a lot going on with regard to PFAS. There's a lot to be learned. There's a lot that has been learned. There's a lot of data gaps as demonstrated on this slide, both in the analytical, on the toxicology, on the properties, on the treatment effectiveness. I think what we've shown you today is that there is technologies out there that have capability of either removing it from groundwater, either through adsorption, ion exchange, other more aggressive processes like electrochemical. There is in situ capability that can be that has been developed that is applicable. I think there's a lot of different. There's a lot going to be learned over the next few years as we continue to do research and development in this area. I would re-emphasize again, not just because we have a treatability lab, but because it's necessary for design purposes, that treatability testing is an important part of this to make sure that you're not creating something worse and that you're able to get achieve your objectives, which themselves are still developing. Last slide just gives you some contact information on the individuals. Again, if you have difficulty, please contact Dennis through the email that you got, and we can get you answers to questions or additional information. As Dennis mentioned, this presentation will be available in the next few days. We'll be sending out to the attendees a link to basically get the slides if you would like to use. Again, thank you very much.
That concludes the webinar, and have a good rest of the day. Thank you very much.